important to do the analysis, power system analysis. Can you see the screen?
Yes.
Yes, sir, we can.
All right, good. Thank you. So power flow analysis, which is also known as load flow analysis. And before I said the power system analysis, power system is the world's most complex man-made system. That's what we say. And when we go and do the analysis, we need to use some tool, because otherwise it's really tough to analyze the power system. Probably you have studied numerical methods. So for example, Gauss-Seidel, Newton-Raphson, all these methods. These numerical methods we use in power system to solve, because usually we'll see when do we use numerical methods? When we have got equations, let's say we have got linear equations or nonlinear equations, we have got let's say there are 4 variables, 2 are known, but 2 are not known, but 2 equations, 4 variables. Then how are you going to solve that? You cannot solve it, okay? If there are 2 equations with 4 variables, okay, you cannot solve it by using the linear approach. So that's why we use the numerical method to solve the problem. And in power flow analysis, we use the numerical analysis tool, okay, to solve those power system problems, okay, particularly. And though Khalil was telling you that it was used for steady state, but it is also widely used for dynamic performance analysis. So in this workshop, within 2 hours, I will try to cover both the steady state and dynamic. Okay, though there are some limitation with the new version of the software to do the dynamic analysis, but with the version 33, we can fully complete the dynamic analysis. But now in my computer, they don't allow to use version 33. They are saying that is outdated, but in your computer, probably you can install and use it, but 34 should be fine. Okay, PSS E version 34 should be fine. And I have shared all the relevant materials, with Professor Salim Bhai and Professor Masood Bhai. I have shared, and also I've shared with Raihan as well. I think he has already emailed to everyone. If you have got that, you can try installing that when I'm discussing this thing. So, so what do we do in power flow study? In power flow study, we usually try to get an idea about 4 things. If you look here, we try to get idea about 4 things, which is voltage angle, real power, and reactive power of the network. We represent the power system in terms of an interconnected system, which will have different buses. When we talk about bus means this bus means it could be a pole. Like we can tell a pole in a network is called one bus. Bus is basically, it's similar to the carrier, okay, like a carrier bus, passenger carrying bus, okay. In power system, bus carries the electrical line, but in the passenger carrier buses, that carries the passengers, okay. So these are the similarities. So what we'll do, we need to know all these 4 quantities of a network to do the analysis of the power network, okay. We need to know the voltage angle, real power, reactive power, these 4 things. Please keep in mind when you do the power flow analysis, these 4 points are really important. That means, so what happened in reality, we know 2 quantity of each buses. There are 3 different types of bus in power network. I'll show you shortly, okay. There are 3 types of bus. For each bus, we know 2 quantities, and 2 are unknown, but we need to know 4 quantities for each buses, okay. That's why we need to use numerical method to solve it. So why do we need this power flow? What do we need to do? If you want to interconnect, as I said, power systems are interconnected system. If you want to interconnect one subsystem with another subsystem, you need to do the power flow study, because the power flow study will tell you how that 4 quantities are. Based on that, you can make decision. Let's say if you want to add new line, new generators, or if you want to add new transmission line, new loads on the system, how the existing system will be impacted, okay? for that reason, we need to do the power flow study before we go for a real life implementation. We need to analyze the impact. That means we can use that for system planning. Okay. So also we can use it to calculate the line flow in terms of active and reactive power, line losses, how much power is being lost. And as I mentioned, we can know what is the voltage across the network. Let's say we can vary the voltage at some buses can vary plus minus 10%. Let's say one is the nominal voltage of a bus. After doing the power flow, if you had a new line, after doing the power flow, if you see that like the voltage at some buses go below that limit, so you can take some additional preventative measure. Let's say you can put some capacitor there to improve the voltage of that bus. Okay, so this is why like it is really important. And when I say power flow study, now I am going to show you the definition. Like when I say power flow study, that means through power flow study we want to know the 4 quantity of all buses in a power network. These 4 quantities are, I told you, voltage, magnitude of voltage, voltage angle, then real power injection P and reactive power injection Q, V delta P Q. Okay, these are the four real quantities, or we can represent them in terms of 2 complex quantities, V and delta, because these are the bus voltage and bus magnitude. So V and delta, we can use that as a complex number, V angle delta. Okay. And similarly, we can represent P and Q as a complex or a complex power or apparent power. Yes. Okay. So we need to know 4 real quantities or 2 complex quantities. Okay, that is what we need. Okay. So if there are n number of nodes, that means we need to know 4n, because for each node we need to know 4 quantities. So 4n real or 2n complex quantities we need to know by doing the power flow study. Then I put some equations. Okay, this is I equals to YV. Y is the admittance, V is the bus voltage, I is the current injected into a bus. Then I try to make it in terms of a generalized way, like if there are a number of buses. So this is basically elements of the Y matrix. Okay, you don't need to worry about those equations. I just try to show you like why do we need that, like why do we need that power flow study. Finally, we got like two equations with 4 unknown. Okay, we got 2 equations with 4 unknown. Okay, 2 real equations with 4 unknown, or 1 complex equation. If I go 1 complex equation with 2 complex unknown. Okay, so that means we have got 2 equations, 4 unknown. We need to use the numerical method, and this is what I told you here. Okay, so if we got 4 real quantities and 2 real nonlinear equations, we cannot solve it straight away. We need to use the numerical method to solve it. Okay, and also the loss, like the loss. If we want to determine the loss, we need to do the power flow study. Okay. So other than that, so finally, I'd like to show you the bus. I was telling you there are 3 different types of bus, okay, in power network. We need to know what are the bus and what are the properties of this bus, what are known and what are unknown, okay? If you look here, we have got 4 quantities. I have listed here 4 quantities and 3 different types of bus. The first type of bus is reference slack or swing bus, or we call it infinite bus as well, okay? Because whenever you do some work, we need to do it with respect to something. This bus is we call it infinite sink, like it can absorb or supply power as required, okay? This is a very large, this is equivalent to a very large system, okay? So, and there will be only one reference bus in the system. And for reference bus, we know V and delta. So we need to specify, when we do the simulation in PSS E, we need to specify V and delta for reference bus. Okay, and and we need to calculate P and Q through the load flow. Similarly, generator bus, we call it also PV or voltage control bus. Okay, and there could be m minus 1, let's say m number of, and basically infinite bus is also a sort of generator, but it's a very large generator, equivalent to a very large generator with constant frequency. And that means there will be m minus 1, basically m number of generators. Out of that, we have used one as reference bus. That means there will be m minus 1 buses that will be basically generator bus in a system. For generator bus, you know, like we call it PV bus as well. That means P and V are known. That means real power and the voltage is known. That means the unknown will be angle delta and reactive power Q. Similarly, for load bus, we don't know V and delta, we know P and Q. So these are different types of buses. And there are a lot of methods to solve the numerical problem. And here I have listed some of those, okay? And I'll show you when I'll be going to PSS E, I'll show you. These are the very commonly used method, but there are more than those methods, okay? I'll show you when I'll take you to the PSS E, I'll show you, okay? So this is the fundamental of the power flow study, okay? This is what we all need to know, because I didn't want to take you straight away to the software and put you in the C, in the middle of the C, and what I'm talking, you don't know, okay? That doesn't look good, okay? That's why I thought that covering this will be good. And also, there are two things. When we do the power system analysis, there are two things which we need to keep in mind. One is static, another one is dynamic. When we say static, that means you don't need to worry about the changes in the system. Static means steady state analysis. I'm sure that all of you solved the differential equation in electrical, I think, or even in computer or other faculties, like other discipline, like we covered the differential equation in the first year, okay? When you try to solve differential equation, we need to know the initial value, okay? If you want to solve the differential equation, you need to know the initial value. Basically, what does steady state do? The initial values are calculated from steady state, okay? And when you solve the differential equation, then you will get the dynamic response. That means you are solving differential equation means changes of a variable with respect to time, okay? So that's why I'll just quickly show you, okay? I'll just quickly show you something related to the dynamics and modeling and all these things. So I'm not going to talk details. I have shared all these materials with the organizer. Yes, if you need that, you can talk to them, okay? So that means, look, this is the commonly used equation that we use to represent synchronous generator in power system, okay? This is the changes in the rotor angle, this is the changes in speed. We call it swing equation, basically. And the full dynamic, and these are the static equation, okay, algebraic equation. That means we need to solve this algebraic equation to solve the differential equations, okay? So the software do it by itself, okay? We don't need to worry. If we use the software, that does it itself, okay? It depends on, this is a third order model. We call it a classical generator model, okay? We use it straight away, okay? We can use it straight away to, we can use it straight away, that software, what types of model we are going to use. And this is also called a transient level generator model, GENTRA, okay? So you will see all this, I'll show you all the similarities when I'm going to talk about the software. I'll show you, okay? And also, I have presented something. If some of you want to go and implement the control, okay, you can do that, okay? I put that as a homework for you. There are 4 activities 0 to 4. Some of these activities I'm going to cover, and some of these I put it as homework, like you can try yourself at a later time, okay? So basically here, during the workshop, I'll cover the simple system. I put the large system as the homework, actually, because modeling the large system will take a lot of time, okay? That's why I just use a small system as a reference. And also, I would like to let you know that, like, knowing this software is going to help you, like, when you'll be going for higher study. If you want to do higher study in the power system, I'm sure that it is going to help you. And even like if you don't study in power system or you do power electronics or something different, but in the domain of power, like knowing this software will help you to get into the consultancy firm, like in US, Europe and Australia. Like most of these companies that are using PSS E or this silent power factory, they are related. If you know one software, you can easily you work with other software. Okay, PSCAD, all this software. But what I'm going to show you, like all these software are much easier than what I'm going to show you here, because I'm going to show you the data case. The network case is easy. You can drag and put the network, put the elements from the network, and you can build a system like as we do in Simulink. Tushar was showing the Simulink, I think, in this workshop. Other softwares are more visual. In PSS also you can do visual, but I'm not going to show you visual. Visual is easy, but I'm going to show you how to model the power system. Okay, how to model power system, like how to model power system in PSS and how to simulate that power system. Before I go to the software, do you have any question related to the fundamental of power flow study? Okay, you can ask me question without any hesitation actually. Okay, and please don't feel shy. So in software, what I'll do, like I'll show you, well, let me share the screen. I'll first show you activity 0, okay? I'll first show you activity 0. If you look, I just, in the beginning, I just provided some overview of the software and all this. If you look, if you install the software, if you open that software, I have already opened it here. So let me show you. When you are going to open it, it shows these options, okay? Case data, and diagram. That means you can use diagram, case data. I'm going to show you case data or network data. So sometimes I use the previous version that shows network data. And let's start with a new file, okay? So I'm going to show you the network data. Let me proceed. So case data, okay. Let's open it. I don't want to save this. No, I don't want to. No, that's it. So if you look, when you install it, says so you are going to install it 50 Hertz or 60 Hertz. Okay, base MBA, that is what we need almost. Like we use by default 100 MBA. That will not affect your simulation anyway. So base frequency, let's say we use 50 Hertz. Okay, so now we got it. So first you need to put some information. Okay, first you need to put some information. This is the software. Okay, first we need to put some information to save it. Otherwise it's not going to save. Okay, let's put one bus to save it, because otherwise you cannot save it. You can save as whatever directory you want to save. You can save as, let's say I want to save somewhere. Let's say RUET. Okay, but if you want to save it without any information, it will show you some error. Okay, so this is the file, and you will see there are different tabs under this thing here. You will see there are different tabs: bus, plant, machine load, fiction. That means it has got all components. It has got all components that a power system need. Okay, so it has got different tabs. If you look, if you just click, it has got different tabs. Okay. So we'll start with bus, but before I start in the software, I want to show you which system I want to build here. Okay. Once I save that, okay, I did it, like I changed it to 50 Hertz. Okay. So after clicking OK, you saw this, I showed you. This is the output bar at the bottom. That means this is the output bar here, actually. This is the output bar. And what happened, like now I want to develop this system. If you look, this is a 4-bus system. Can you see the PDF? Yeah, if you see it, like you will see 4 bus, and it has got 2 generator and 1 load. This is represented, this arrow is represented as load in power network. Okay, this is a single line diagram. That means we have got 4 bus, and the specification of the system is given here, like consider bus 1 as infinite bus, bus 2 as generator bus 3 and 4 as load bus. Even the generator bus and infinite bus are defined, you can assume that all remaining buses are load bus. Okay, even it is not said. So let's put it, there are 4 buses in the network. Let's put the bus number 1, 2, 3, and 4. There are 4 buses. Bus 1 is infinite bus. Let's put it infinite. You can put the bus name. It is not mandatory, just for your information, so that you can understand it later. Okay, you don't need to put it even. Okay, bus 2 is a generator bus. Bus 3 is a load bus. Bus 4 is a load bus. Okay, so once we got it, like I just put 4 buses. For generator bus, if you look, P and V is given, because for generator we know P and V, and for infinite bus, V and delta given. That must be given. Okay, we know V and delta. For load bus, 4 we know P and Q. And the network data, that means the line impedance of the line, that means between 1 to 3, 3 to 4, 3 to 2, or 2 to 3, these are given. That means we want to develop this network into PSS E. Okay, let's first define the buses. Okay, now how PSS E will know which bus is infinite bus? We put 4 bus. We put 4 buses here. Okay, but I haven't defined which bus. I have written the name, but PSS E will not, as I said, you can put it or not. But how are you going to define the buses? To define this, like we need to define code. For infinite bus, we use 3, and for generator bus, we use 2. Okay, these are the code that we need. Okay, so that means if you look here, power flow data changes for bus 1, that means the infinite bus. Okay, bus 2 generator bus. Okay, so this has been defined. All remaining buses are load buses now. Okay, now if you look, there are different zone, area, and all these things. Usually industry people, they use this. Okay, section with section, because that helps them to know who is part of the network actually. Who is part of the network. Okay, so you can put all this information. If you are going to work for an industry, you can put all this information. Who is the owner? Like there are different owners. That's why it could be a PCB, or it could be someone else. Okay, or some private companies. Okay, you can put all this owner, and you can number those owners. Okay, depending on, or you can sometimes what happen if you go to work for industry, you can straight away, if the network data is there, you can straight away open it using the raw data file. If you look here, if I go and click open, like there are a lot of different file format. The first one is called CNV, SLD, and all this. Our raw is the normal file that usually the equipment in power network, we can capture that through some SCADA system. We can capture the raw data file of the network, and we can straight away use those data just by opening the raw data file. Okay, in that case, you don't need to really build this new system. We define the code. Okay, we define which bus is what. Now here in this tab, you can look the voltage and angle we can put. We can put only the voltage and angle of different buses. That means we know the voltage and angle for infinite bus. Okay, that means let's go and have a look in the activity 0 file, page 4. I have provided that information. For infinite bus, voltage is 1 per unit, and the angle is 0 degree. That means by default it comes 1 and 0. We don't need to change it. Okay. For generator bus, if you go and look back for generator bus, I have given the voltage as 1.01 per unit. Okay, that means we need to put it for generator bus. It's 1.01. 0.01. Okay. So that's pretty much for this tab. Okay. Now we need to go to machine tab. After this bus tab, we need to go to machine tab. And as I said, like there are two machines, two generators. Okay, though one of this is infinite bus, but if you look, there are two generators, one at bus 1 and another one at bus 2. That means let's create that machine. Okay. See, new plant created at bus 1 and another one will be. Sorry, it's restarting. Yeah. For some reason it was hanging. Okay. Let it restart. Okay.
Dr. Apel, can you hear me?
Yes, yes, I can hear you.
Yeah, I like to draw your attention into the PDF file. I think something is confusing there. The definition of bus 3 as the infinite bus. Could you go to the file, please? Well, this thing I'm not quite clear because from this figure it is look like the bus 3 is the infinite bus. But the statement is
Bus 3,
saying
no, I didn't say bus 3 as infinite bus. Let me show you. Yeah, here I said bus 1 is infinite bus.
Yeah, this thing I'm talking about. It is written here the bus 1 is the infinite bus, but is it actually? Because it looks like bus 1 is also a general bus.
But as I told you, when I was covering this material in my PowerPoint, I told you here, like basically there are m number of generator actually, but one of these generator used as reference bus.
Oh,
that
okay.
means, yeah, this is what I told actually. Okay, does it make sense? Is it clear?
Yeah, thank you.
All right, thank you. So let's go back. Okay, so I want to restore the previous session. Okay, so let it open. Yeah. So it's taking a bit long. Okay. Okay, all right. So the good thing is like you can still get that recovered. Okay, wherever you did, you can. If it's suddenly closed, it will automatically recover. Okay, so I've got it here. So let's machine. So let's go to machine tab. And also you can put the base KB. I put it 11, but that will not affect your result. Yeah, all this will not affect your result anyway. Okay. So let's put machine now because that was troubling. Let's put 1 and another one is 2. Okay. So 2 machine created. And for generator bus, as I told you, for infinite bus, here we need to put the P and V information. Okay. One of this generator is infinite bus, and for which the voltage is 1. But for other bus, the voltage we know P and V. That means we need to put P and V. P is the generated power, P generator. Okay, and P gen is given as, if I take you there, P gen is given as 15 megawatt. Okay, and the voltage is given as 1.01. That means for this step we put only P and V for the generator. That means we need to use P here, V here and P here. That means P is given as 15 megawatt. Okay. Megawatt and V is given as 1.01. Okay. And you can use I want to bring some attention, like most of the generators in real time, they have got minimum and maximum generation capacity. Okay. what is the minimum it could minimum for operating condition, what is the maximum. You can put that limit, especially for the activity, like for the activity 1, which I put it practice yourself. I ask you to put some limit, okay? For generator, P limit and Q limit are given. For Q, this is the limit, okay? And if you got other source impedance, you can put it, okay? You can put the source impedance. If it is coupled with the transformer, like you can put the transformer resistance and reactance here. But I try to make it simple here, okay? All this information can be put there, okay? So once we put bus information, machine information, after putting this machine information, the plant will be automatically populated. If you look, the plant has been automatically populated. We didn't do anything in the plant. All this information has been automatically populated. Okay, and if you look here, for the machine, we don't know Q. Q is 0. Okay, we don't know Q. For the infinite bus, we don't know P and Q. But after running the load flow, all this information will be changed. I'll show you. Okay, after running the load flow, all this information will change. But still now we didn't finish the network modeling. Okay, we just put this information. Okay, we put this information now. Okay, now still we need to put this information. Okay, that means let's go to the load tab, and we got load at the bus 3 and 4 are load bus. I say bus 3 and 4 are load bus, but there is no load connected. This is an intermediate bus actually. Okay, like there are some poles in the line in the network. You will see that no load is connected. It could be a pole like that. Okay, from there is a branch and there is a generator. Generator is coming to that bus. Okay, so what happened then? Let's put the load information. We can put P and Q there. Okay, P and Q for bus 4. That is given as 10 megawatt and 6 megawatt. Okay, so now let's go to the load tab, bus 4. Okay, so bus 4, and we got P and Q, P load and Q load. If you look, P load and Q load, we got P as 10 and Q as 6. Okay, so we got P and Q like, but if it is a constant, we consider that this is a constant power load. It could be a constant current load. Okay, IP and IQ, or it could be a constant impedance load. Okay, there are three different types of load in the network. Okay, so we can put depending on the load. Here I have considered constant power load. That's why I put P and Q. Okay. And there could be fixed shunt and all these things. I'll show you later on. Okay, there could be fixed shunt and all this. Later I'll show you in another network. I'll show you. Okay, how there could be induction motor load and all these things. There could be. Okay, and there could be connected. But let's stick with the simple one. Okay, next one I'll show you a bit complicated. We put this information now. The network data. That means the impedance of the line, that means between 1, 3, 2, 3 and 3, 4. All these are given here. Let's say first start with 1, 3. Okay, 1, 3 or 3, 1, they are same actually. 0.02 and 0.3. That means we want to put a branch now. Let's click on branch. Okay, from bus 1 to bus 3. And line resistance is given as 0.02 and reactance is given as 0.3. Okay, but there could be X, because if you look at the transmission line modeling, there could be shunt impedance, okay, shunt admittance. So we can put that shunt here. Okay, so but here I have neglected this. Okay, so we put this information, okay, for line 1 and 3. Now let's put for line 2, 3, which is given as 0.1 and 0.4, 0.01 and 0.4. That means line, sorry, that was 2, 3, is that right? That was 2, 3, 0.01 and 0.4. Let's put from line 2 to line 3. That is given as 0.01 0, 1, and other one, sorry, 0.4. Okay, so we put 2 lines. Now let's put the third line. Third line is a completely reactive line. Okay, we have got only reactance, we got 0 resistance, let's say. Okay, so that means the R will be 0 and X will be 0.02. That is 1, 4, I believe. Yeah, that is between, sorry, 3, 4. Okay, 3, 4. We got 0.2 only X. We got 0.2. Okay. So this is what we put. Okay, this is the information it has given. But there could be multi-section line, there could be switching device, there could be mutual coupling, and all these things there could be. Okay, but here we will just put AC line. There could be 2-winding transformer, 3-winding transformer. All these things could be there. And if you look at the manual, it's a couple of thousand pages. So if you, by going to the manual, it's really hard to understand. If you want to put facts, you can put facts devices. Okay, all the information are there depending on the network like that you want to build. Okay, that could be on. So if you look, so these are the information. Okay, these are the information that has been provided for the network modeling. Okay, steady state, and this is what we call a steady state model. Okay, we have now developed the steady state model, and whether this model works or not, how do we know? Like as I told you, like if I take you to the bus section, okay, if I take you to the bus section, you will see that like the voltage here, all voltages are 1 per unit, the angle, all the angle are 0, but this will be changed. This is what you will see changes, okay, after running the load flow. If I take you to the load section, P and Q are given, but for this, the voltage will change here. Voltage and angle will change, particularly for bus 3 and 4. And for machine, if you look, only we know the P for the generator, but for all other buses, we don't know anything, okay? We don't know Q and we don't know P for the infinite bus. So after running the load flow, we'll know all the quantity. So if you look, there are different tabs here. At the top, there are different tabs: data grid, power flow, short circuit, OPF means optimal power flow. This is the dynamics. I'll show you dynamic shortly. Yeah, after this, I'll show you the dynamic simulation. Though I cannot completely show you because of the limitation of this free version, okay? But I cannot use the professional one because we use network licensing, but for that I need to be at uni, okay? But I'm showing you from home. But anyway, but you will get clear sense. What I can tell you, you'll get clear sense of what we are going to do. So if you go to, because we want to do the power flow, okay, that's what we talk, okay. If you look, after clicking on this power flow, if you click on solution, then click on solve. There are a lot of different options, but click on solve, okay. When you click on solve, then this window comes, actually, okay. When this window comes, so what happened? You will see Newton method, Gauss method. Under Newton, fixed slope, decouple Newton, full Newton Raphson, decouple Newton Raphson. Some of this method I told you here, okay? Some of this method I told you, Newton Raphson, decouple Newton Raphson, fast decouple, okay? Some of this method I told you here. That's already there. So if you look Gauss method, Gauss-Seidel, modified Gauss-Seidel, robust solution. If you look, fixed slope, decouple Newton Raphson, full Newton Raphson again, DC solution or DC power flow, okay? There are different methods, okay, to solve it. Let's use the Gauss-Seidel method or Newton Raphson method. That is, these are the methods we most commonly use, okay? But the difference is the iteration, okay? Like the number of iteration will be less. Gauss-Seidel method, it will take more iteration. It will take around more than 10 iteration. But if you go with Newton Raphson, it will take only 3-4 iteration, okay, to solve that problem, okay. Let's solve it with the Gauss-Seidel method, okay. Okay. So risk tolerance, if you look at the output, it shows a lot of different things, but at the end, the summary, if you look at the output bar, risk tolerance in 14 iterations, okay? Largest mismatch 0.2 in the active power mismatch, they find it. There's some error, okay? There's the error that's showing. Largest total system mismatch 0.04 MBA, that's not much actually we say. And this is the it risks solution, it risks tolerance. But if your modeling is not right, it will say that it has terminated after a few iterations. That means the model that you did, that's not correct. That means when it says it risks tolerance, that means it is the solution that we got. Yeah, it has a solution actually. And now let's go back to the bus. As I told you, this was one point. The generator bus voltage will never change. This will not change after running the power flow. This too has not been changed. It was known whatever the value we have got that same value. But if you look the bus for this one, okay, for generator we know P and V, but for load we know PQ. That means we need to know V and delta. But if you look, the load bus voltage change, load bus angle also change. Okay, after the power flow. And if you look here, the generator rotor angle changed, but for the infinite bus, it has not changed actually. And generator rotor angle changed, but the voltage is same. Now let's go to the machine tab. See, we put 15 megawatt for generator, it's still 15 megawatt. We didn't put any reactive power. We got reactive power here. For the infinite bus, we did not put the P and Q, but we got Q and P here, P and Q. Okay. Though it is negative because, as I told you, infinite bus is an infinite thing. It can consume or deliver power depending on the requirement. Okay, depending on the system requirement. Because in the system we saw that there are 15 megawatt of load. I put load 15 megawatt. 6 and. Sorry, we got like a 10 megawatt of load, but we got generation of 15 megawatt. That means the 5 megawatt has to go somewhere. That is what it is going here. Okay. And for load, if you look for the load, we got Q as 6 megawatt, but for the generator, it's generating around 4.5, and it's like the infinite bus is providing reactive power but consuming active power. Okay, as it is an infinite thing, as I told you. So this is the load flow. This is the power flow study. That means we know the voltage and angle. We know PQ for all buses. Does it make sense? Any question up to this point? What I said, did you get it clearly?
Sir, I think we got it clearly.
Okay, all right. So now I'll show you the dynamic simulation, but before that, before the dynamic simulation, I want to show you activity 1, okay? And there you will see, because I want to quickly clarify a few things from here, okay? Though I'm not going to show you the model for that activity 1, okay? But what I want to show you, like this is something that I put for practicing yourself, okay? So if you look, this is the IEEE 30 bus system. I have got that SAP file. If you need it, I can share with you with Khalil. He can share with everyone. But you can do it, okay, by yourself. If you look, this is a more complicated system. It has got 3 winding transformer, 2 3-winding transformer, like at some places in the network. Okay, this is one of the places. Okay, where it has got 3 winding transformer. And it has got another 3 winding transformer, and it has got like all the data are given, like for, we have all, I have told him like bus 1 is the infinite bus, again I said angle is given. For other bus, let's say, for example, this is the generator bus, okay? Bus 2 is a generator bus, and at the same time, load is connected. Please consider this bus as generator bus, okay? Because PGen, it's a generator could have local load, okay? So it is more a practical system. This is basically a, we call it New York power system. This is the modified representation of New York power system. This is an IEEE test system. When we do research, we usually validate our results using this test system. But what I'm showing, there is not at the research level. I'll show you at the advanced level, okay? Within few moments, I'll show you something at advanced level. Network data, that means the bus given, here B is also given, that means the charging. That means for this network, you need to put, when you put the branch information, you need to put B as well. Okay. And also, if you look, this bus 24, 10 and 24, it has got shunt capacitance, okay? Which is, this is in per unit. If you use 100 MVA as base, you need to multiply with 100, okay? Because in the, all this given are in per unit. But when you put in PSS E, and let me show you, fixed shunt, let's go to the fixed shunt. Shunt, okay. So if you look here, we need to put it in megavar. Usually shunt capacitor, we consider that as ideal. So the shunt megawatt is 0, but shunt megavar is, we need to put just the value in per unit. You need to multiply with 100 because we have considered the 100 MVA as base, okay. So that is what we consider. So when you do go and develop that model, so the first thing that you need to do is, very first thing that you need to do is you need to put the bus number, all 30 buses. That means, let me open a new PSS E for the activity. Let me say, I'll show you, it's not going to save. Okay, I should put 30, okay. Let's see, okay. So what do you need to do? First, you need to put 30 buses. Sorry. So first you need to put all 30 buses. Like this, okay. You can just put number and down arrow in your keyboard, okay, easily. So what I'm doing, I'm putting a number in one hand and using the down key of my, down arrow of my laptop key, okay. So you can easily do that, okay, 1, 3, 1, 4. So you need to put all this bus number. Then you need to put the voltage and all this information. You will get the voltage and all this information, the network information from here, all this voltage information, whatever bus you got, you need to put all this voltage information. Then you need to go and create machine tab, okay? So if you look, this is a machine tab. And also in this network, there are a few things I need to tell. We got synchronous condenser. Let's say in bus 5, we got bus 8, 11, and 13, okay? Bus 5, 8, 8, 11, and 13. You will see some stress thing in these two bars. QG is given, PG is not given. That means these are synchronous condenser. If you look, these are condenser. Okay, 5, C is condenser basically. If you go 5, 8, 11, and 13, 8, 11, and 13. All these have got one synchronous condenser. Synchronous condenser in network is nothing, it's overexcited synchronous generator. It provides reactive power. Instead of active power, it provides reactive power. We use the synchronous condenser for the voltage control. So this network is basically more variation. There are more variation in this network, okay? We try to make it a bit more complicated, but I want to show you the dynamic modeling because I thought that I cannot cover this whole model because it's going to take itself 1 hour to develop that model if I go in and do it, okay? And that's why I told 3 hours, but yeah, 2 hours are given, so we will finish it. We will finish in 2 hours. But these are the few things that you need to keep in mind. I just wanted to clarify, like we need to put fiction. You need to use, so if you go to branch, you need to put 3-winding transformer because you have got some 3-winding, okay? And that's pretty much. Other than that, and also generator, like all this synchronous condenser will be generator bus as well. With bus 1 and 2, okay, there are more generator bus, 5, 8, 11, 13. Bus 1 is generator bus because this is an infinite bus. Bus 2 is generator bus, okay, because this is a generator bus. We have got PG. And if you look, there will be 4 more generator bus. And for this, you need to put key. You don't need to put Q actually, okay? Generator bus, you don't need to put Q. I have mentioned Q just to check your result here. These things you don't need to put. If you go for the synchronous condenser, let's say for the generator winding, let's say bus and equipment, if you go to machine, just put the value of, for bus 5, 8, 11, and 13, put the value of Qmax and Qmin. You don't need to put all this information. Let me share you, yeah, the model that I have already developed, okay. I will show you that one. Let me open it. Another thing that I did here, you can use, instead of the 3-winding transformer, you can use branch, because if you think difficult, because in previous version we cannot use the 3-winding transformer. This is an update. That means you have got, when you see 3-winding transformer, basically it's 3 branches. You know, one branch is 12 to 3, another one is 2 branch basically, okay, so 3 nodes, 12 to 13 and 4 to 12. Similarly here, 9, 11, 10, 9 and 6, 9. These are 3-winding. So all these parameters are given, so you can put this as branch. Instead of putting a 3-winding transformer, you can put all these as branch. So if you look here, this is the 30 bus. I'm showing you the 30 bus one that I have already developed. Okay, this is the 30 bus, all 30 bus I put. If you look at the machine tab, 1, 2, 5, 8, 11, 13. And for the machine, if you look, or generator, if you look, only I put 40 megawatt. But for this QGen, I did not put any QGen. For other, I just put the maximum and minimum limit of the reactive power as provided here. I provided the maximum and minimum limit of this, okay? So I put load information is given as well, okay? Load information, if you go here, all this PL and QL given, I put all load information. Then I put fiction, look, 19 and 4.3, 19 at 10, 24 at bus 24, 4.3. Basically, I multiplied whatever I have got here. I multiplied with 100 because this is in per unit. We need to multiply with 100 because we consider the base as 100. Okay, that's right. And then we put all the branch information. And putting branch information is really critical because that takes a lot of time actually. Okay, so if you put all those information, if I take you to the branch, AC line, let's see, all these informations are here. Okay, I did not put 3-winding because I put it in the form of branch. The previous version was not allowing me to do that. Okay, so this is what we have got. If we do the power flow, again, if we go back and look at the power flow, look, all these angles are 0, 0, 0, okay? All these are 1, 1, 1, 1, 1, or something like that. Some of these 5, 8, 11, 13 are 10. If you look 5, At 5, it's a 1, oh, sorry, 1.01. But if you look at 11, it's 1.082. And 13, it's a 1.07, okay? So these are given here. So if I do the power flow of this one the same way, let's use the big one. So let's use neutron rates one, okay? Decoupled neutron rates one. Okay. So even with this large system, we reach the tolerance within 13 iterations, okay? So that means it reached the tolerance within few iterations. So that means it converged. So if you look, all these values have changed. Voltage angle and everything has changed now, okay? And the code for these buses has changed now because it was 2, I put it, but all this has changed to -2. That means it's not generator, it's not a typical generator, it's generating reactive power, okay? So if you look, and if you go to the plant tab, now this value has changed. If you look, this Q value has changed now, okay? So all these bus voltage and everything has changed, like a P and like for example, for this one Q has changed now, Q gen, it was 0 before. That means now we know everything. And now here the infinite bus is supplying power. Look, here it's supplying power because the load demand is high. All right, any other question? So if not, so then we can probably have a break for 5 to 7 minutes. Then I'll take you to the dynamics, take you through the dynamic simulation. But I'm sharing you this sub file for IEEE 30 bus. Okay, you can practice yourself, or you can like I'm sharing through the message chat box. If I can attach it, so I'm attaching it. Okay, so that you can straight away download. So you can. So I have just attached it here. Okay, so you can download it and you can practice it later on if you want. Okay. So Khalil, can we take break for 5 minutes or something like that?
Yes, sir, we can. We can.
Okay, then let's take a break for 5 minutes because that will so that we can start with fresh mind. And but before that, like any question before we go on break, is there any question? All right, we'll talk in 5 minutes. Okay, I'll be back in 9:25. So thank you again. Yeah, so what I would like to see you now, show you now, like I would like to show you some dynamic simulation. Okay, then if you look at the file that I sent you, particularly activity 2, okay, the series of files that I sent you. In activity 2, like I used a different system. Okay, I used a different system. I just try to make some variation in the system so that you can practice different system when you are practicing this software. Okay, here this is a system that we normally use for voltage stability study. Yeah, this is taken from a book called Voltage Stability by T.V. Karsam. Okay, he's an European author. Okay, so we took this system from his book actually, and when we do this study, like first we need to do the static model and then we need to do the dynamic model. So whatever I presented so far, that covers static model. That means this is if you look, this is a 4-bus system again. Okay, this is a 4-bus system, bus 1, 1, 2, 3, 4. So bus 1 is infinite bus 2 is generator bus 3 is again another intermediate bus, and bus 4 is a load bus. And if you look, here are 3 different types of loads are connected. One is fixed shunt or shunt capacitor. One is like impedance load, constant impedance load, or normal load, you can say, and another one is induction machine. Okay, so these are 3 different types of loads that we have got on this particular bus. Okay, and in the PSS E, like the material that I sent you, I have already done the static and dynamic model. I'm not going to repeat the static model here, but just I'll open it. Okay, I put all those information in this model. Okay, I put all those information that we have got for static model. Okay, friction 250 MVAR, megavar. We got transmission line data. We got two parallel transmission line. If you look 1 3 1 3, so that means we need to put 1 3 and 1 3 twice actually. Okay, so let me open that static file first. Let me open that. I have already sent you. If you look at PSS file, you will see that SME1 original.sec. That's the file. Okay. So it's opening. Okay. It's not going to crash. No, I don't want to save. So if you look, this is for generator. Okay. And I have defined all this generator. And if you go to machine, okay, 1 and 2, and if you look at load, okay, I put two loads here. One is for, if you look, two loads. One is for machine, induction machine, and another one is for this constant impedance load. That means these two loads. If you go to the load tab, one load is this 1485 megawatt. Another one is like 145 megawatt. So this one is this is basically load 42 is this is not 145 actually. There is a typo. So okay, I have corrected it anyway. So if you look here, I haven't used it. This is basically 15. 145 is basically 15 for the second one and 5. Okay. Sorry about that. This is a typo. So this will be basically 15. So there will be not, yeah, this is 15 and 5. And if you look the fixed shunt, okay, 250 megavar, I put that as a fixed shunt. So fixed shunt at bus 4, 250 megavar. Okay, that's what I put. And let's say with the branch, so I put transformer, two transformer, one between 2 and 3, two winding. It was in previous version, so I can put it. Yeah, that's why I put it. So between bus 2 and 3, bus 3 and 4, I put transformer. Okay. So I put transformer data is given X. So for this transformer, I put the impedance, sorry, reactance. Okay. For the two transformer 2 to 3 and 3 4. If I take you there, so if I take you, so if we go there for transformer, sorry, yeah, so this is where I put the X, okay, transformer data. This is where I put it here. So 0.016 between 2 and 3, 0.004 per unit, okay. So these are the information that I put there, okay. Transmission line, 1 3, we have got two parallel line. That means this two parallel line, I put it, okay. This two parallel line, 1 3 1 3. If I take you to the AC line, 1 3 1 3, okay. So I put 0.054 for both of this line, okay. So this is how we build this system. This is the static model, okay. That is what I have been showing you. But when we do the dynamic model, we need to follow some steps, and that is what I mentioned here. If you go and look at activity 2, so these are the dynamic information. These are the, like, if you look at the differential equation in the slide that I put, all this differential equation involve this. Usually in generator, we have generator, then we have got excitation system, and we have got governor, okay? So these three part forms, okay? Okay, like the complete generator model. Okay, this is the related to the generator data. This is related to the excitation system data. And this is related to the governor data. That means when we do the generator modeling, we need to put all those information there. And this generator, I ask you to consider this generator as a transient level generator, or based on this information, like if the model is not given, based on the parameter that has been given, you can assume a model. Okay. So how do we do the modeling? So when we do the modeling, we create a file called DYR file. Okay, called DYR file. And how do we create it? If you right click and go to new and put a text document, let's say I put it through it. Okay, .dyr. Change the extension .txt as dyr. It will change it. If you look, the icon has already changed. Okay, so this is the this is how we create that dyr file. Then within the dyr file, okay, we put some information. We put the modeling information. We put all those parameter information. That means the parameter that has been given, the parameter for this model, dynamic model, that has been given. Okay, that's what we put. Okay, that is what we put there, and we complete that dynamical modeling. And now, what is the sequence we are going to put, and how PSSC will read those data from the DYR file? Okay, that is what important. And for this, you need to know the sequence. You cannot remember it. Like if you look, you cannot remember that. That's why I put it, like if you go to start menu, CML, all programs and all this, I'm going to show you. If you go to the PSSC documentation and look at the model library, you will find it. Okay. I'm going to Babano. Sorry, my son. So if you look at the model library, you will find the process of way to put those data. Okay, and I'll show you, like yeah, I'll show you what I have shown you here step by step. I'll show you there. Okay. So if you click on the start menu of your computer, okay, then if you go to Siemens PTI, okay, in your computer after installing, you will see it. Then I've got two versions. One is 33, though it is not working. So you will see everything 2 times. That's why. Okay, copy runtime libraries twice, everything 2 times, because I still keep the other one. Documentation 2 times, but in your computer there will be only one documentation. If I use any of this, open any of this, so basically this file will come up. And if you look, this is the whole manual actually. All these individually, 200 pages actually. All these individually, if you want 200 pages. This is 1500 pages. Okay, that's the operational manual. It's huge actually. It's really hard for someone. Okay, it's really hard for someone like who doesn't understand, or who doesn't like yeah, so who doesn't like have prior experience. It's really hard. If like it's this nightmare if you go through these 1500 pages, unless someone teaches you. Okay, so it's really a nightmare. So what I want to show you, yeah, let me take you to other one. Like we need to go to the model library to do the dynamic model. Okay, so let me go back, because I have to go back again. Yeah, to open that, because just change it. So we'll go to these cheat sheets are new. It was not there before anyway. So if I click on model library, because that is what our interest, this is basically the dynamic modeling. Okay, so if you look, this is the different types: generator model datasheet. This is compensator, stabilizer, minimum excitation. Whatever model we use, okay, all models are here. Machine and wind model protection, 2-terminal DC, everything, all dynamic data sheets actually. This is all dynamic data sheet. Okay. So that means the way we will be using this dynamics. So we need to first, let's see, we want to model the generator. That's why I click on generator. And you will see different variations of models. Okay. When we say generator, these are basically simple generator model. And for infinite bus, we use basically classical generator model. Okay, Gen CLS. That's why the DYR file that I have, okay, you will see the generator. The first one you will see Gen CLS. There is a classical generator. Okay, there is basically a classical generator. That's what you will see. So that means now let's, for the generator one, let's use that as a classical generator, Gen CLS. Okay. So this is the first you need to put IBus. IBus means bus number, then Gen CLS, then the ID. There will be an ID created when you go. If you go to the, let's say, if you go to the machine tab, there is an ID. For both generator, the ID is 1. Okay. So if I show you here, see, first we put the bus number, 1 is the bus number, then we put Gen CLS, then we put the bus ID. Okay. Now, other information, con J condition or J2, J plus 1. That means you need to put inertia and, sorry, Gen CLS, let's go there. Sorry, I clicked somewhere else. So, if you look here now, if you look here, after that you need to put inertia and damping. I have considered this is an infinite C. It doesn't have any inertia, any damping. Okay, that's why I put 0, 0. Okay, but you can put some values if you want. But if your manufacturer or if your companies provide that value, you can put this value here. Okay. Let's go to the second generator. Okay, and as this is a classical generator, usually each generator will have generator model, exciter model, and governor model. Okay, and if they come up with a stabilizer, we need to put stabilizer model as well. Okay, but let's say Gen CLS doesn't have anything. It's just a sync bus. Okay, it's just an infinite bus. Okay, it doesn't have anything. Let's say for the second generator, I have used a transient level generator model. Gentra, I say that is. Gentra. This is a transient level generator model. Okay. We have used this model, and again, if you go, this model represents EQ prime, speed, and angle. Basically, this is the thing. This model represents these 3 equations, basically. These 3 states, these are 3 states, delta, omega, and EQ prime. Okay, this is basically a transient level. But if you go for the other generator model, let's say Selenium type model, it depends on like what parameter you have. Okay. If you go for Zencel, you will see 2 more additional steps. Okay, it considers the flux linkage, subtransient and damper winding flux. This is the subtransient. This is transient. This is subtransient. Okay, so it considers subtransient and like and damper winding, and this phi is damper winding flux. Okay, it is more detailed info here. So you can select round rotor generator. This is another type that we commonly use, round rotor. It will have, it will have a bit more, one step more. Okay. It has got both damper winding in like real and imaginary, but it doesn't consider the subtransient. It considers both axes, D and Q axis. Okay. And the sequence of the parameter is, here is the sequence of the parameter that we put. This is the sequence. First, you need to put TD prime, TD double prime, TQ prime, TQ double prime. H is the inertia, speed, damping, XD, XQ. This is the sequence that we follow. That means if we use a transient level generator, Gentra, first we need to put TD prime. Okay, if I show you, Gentra bus ID is 1, TD prime is 8. If I take you to the PDF file that I provided for this activity. I give you TD, this is 8 seconds, okay, TD and TD prime sum, okay. Then after that, after TD prime, so what? After TD, oh, Hayes D, okay, Hayes is given as 3.5, D is 4, so that means 3.54. You're using the sequence you put after that XD, XQ, XD and XQ are same, that's why I put the same. Some parameters, that's the ideality factor and all these things, acceleration factor. Okay, this is the saturation. We put saturation sometimes 0. We put some values of the acceleration vector. These values are not provided most of the time. But if you got a generator manufacturer, they put all this information in the generator manufacturer menu. Okay, that means you can have this, when you put all this information, you got the dynamic model of the generator. Now let's go to the exciter model. Okay. Similarly, what we did, we went to the excitation system, and we use this IEEE 1992 SC4A type excitation system model for this, but you can use different one. Okay. And we put the parameter in this sequence the same way, like which bus the exciter. The exciter is connected with bus 2, okay, for the generator, because it's connected with generator 2. That's why it is with bus 2. Then we use all these parameters sequentially, like in this table. That means you need to have clear idea of what model you are going to use or what model you are provided. And if you cannot find out the model, if you when you do the research or when you do the analysis, if you don't know which model are you going to use, try to map the parameters. The parameters are provided, whatever the parameters you have got available. Try to map the parameters with this table, and whatever table it fits, use that as model. Okay, let's say instead of this, your model might fit, if you've got the parameter, that model might fit somewhere in this model. Okay, you can use that. So there is no hard and fast rule. Then turbine governor. Okay, we use a governor model. We use TGOV1. This is the commonly used. Whatever I have shown here, all these are commonly used model. Okay. So once you put all those information, whatever information you have got in your dynamic model, based on what you want to do the dynamic modeling. So I've got the generator data, excitation system data, governor data. I put all these here by following the sequence in the model library, dynamic model library. This is the model library. Okay. Even if you look itself, there are 748 pages. Yeah. So it is really, really hard if someone is not telling you what I want to say. It is really, really hard. And usually industry people, they arrange this, like even in Melbourne, they have been arranging regularly some people for 2 days, like comprehensive 2 days, like you'll be doing hands-on, they charge $2,000 usually for all this training, $1,000 per day, which is around 60,000. Yeah. So yes, but when you go and enter into an industry, they usually send for those training actually. Okay, but if you know this beforehand, yes, you will be really attractive to those industries. So this is what we do. Like once we do this dynamic modeling, then what we need to do, like we have done this static modeling, we have prepared the dynamic modeling. Now, how are we going to do the dynamic simulation? Okay, now in the next 15 minutes, I'll show you how we do dynamic simulation. All these steps are provided here, but I'll show you here as well. All these steps I have provided by drawing all through by capturing all these. I have put all these steps here. Okay. So, and also how to do simulation, I have provided everything here, okay? But I'm not, you can follow it at your own time, but when I'll be doing it, yeah, I'll be definitely following those steps, but I'm not going to come back here and show you again and again, okay? Because that's not an efficient way to show you, okay? And definitely in 15 minutes, it's not, yeah. So first thing is, you need to make this static system ready for the simulation. Okay, you need to make this static system ready for the simulation, that it will be linked with your dynamic model. Okay, you need to make it ready for that. So what do we do? First, we convert the load and generator. Okay, convert generators, convert loads. For this, we go to PowerFlow as I showed you. We need to go to that and then click on convert. Okay, so whatever loads and generator we have converted it because it used as a normalized system. It solved the system as a normalized system. Okay, so that all the generators and loads are in the same space. So then we go to PowerFlow solution and we need to follow some steps. Okay, order network for matrix operation. That means we need to make this ready. That means when we click on this, it will create an Y-bus matrix. Okay, it will create an Y-bus matrix. Order network for matrix operation. Okay, assume all branches are in service. Okay. So then we need to go again there. We need to factorize the admittance matrix. Once we did it, we need to factorize it. Okay, we factorize it. Then again, we need to follow one more step. Solutions. Solution for switching studies. Because when you do the dynamic simulation, that means we apply fault and we clear fault. That means there will be switching. Solution for switching. We need to make the system ready for the switching. Okay. You can use flat start or voltage as a vectorized start point. It doesn't matter actually. Let's factorize it. Okay. It's ready for the dynamic simulation and it will be linked with the, now if we open the DOIR file, this DOIR file where I have created this model. Okay. So if we open that, so that will be linked with that network data. Okay. So this dynamic data is here. So let me clear it. Okay. So that it doesn't duplicate actually. So now I am opening the DOIR file. Okay, now it will ask for this compiler. But what I would like to tell you, in the full version, you don't need this compiler. Okay, in the full version, you really don't need this compiler. But again, if you don't have this compiler, you cannot run the simulation. Okay, you cannot run the simulation. Let me put this compiler. Okay, CC1 is for connect. Okay, CC1 is for connect. It says this file already exists. Do you want to replace it? Yes, I want to replace it. So this is, I will put the CT. Yes, but in the previous version, it doesn't show like that because we must need to put that. But this version, like it has already got it. Okay, in the full version, I mean, that's why it is saying that replace. Okay, so now it will open. Okay, so if you look for the generator, we got Gentra, ECS4, TGOG, and all this, we got it here. But before we want to do the before we going for the dynamic simulation, okay, we need to define the channel, like what responses of the system we want to see. Let's say if we want to see the line voltage of the generator, okay, sorry, let's say not line. We want to look at the bus quantity. Setup, yeah. Bus quantity, if you want to see generator 2, you can select whichever response. Let's say I want to see the voltage, yeah. You can select a different thing. You can select frequency if you want. You can select voltage angle if you want. Okay, it's up to you. Then once you did that, like you can select some other machine quantities. Let's say you want to look at the rotor angle, speed deviation, rotor angle, all these different quantities. This is the speed is basically speed deviation for the central generator. Yeah, you can see it's up to you, like whatever responses you want to see. Okay. So we define the channel. Now we'll go to simulation, perform simulation. What do you need to do? You need to select an output function. I just say that, okay, it's a dot out or something like that, okay? So it's 0. You need to change it to 0 and you need to click on initialize or yeah. If you see that initial condition check is okay, that means your dynamic modeling is correct. If this initial condition check is not okay, that means there are problem with your dynamic model, okay? That means at every stage you can check whether whatever you have been doing, that's correct or incorrect, okay? And let's now run the system up to 1 second. Okay, it's running, okay? All those responses are like the data are given here, okay? All this data are saving also at the file ruet.out, this file, okay? That data has been saving here as well. Now I've run the system up to 1 second, then I want to apply fault. Let's say I want to apply fault at 1 second. Apply disturbance, click on apply disturbance. I want to apply fault at 1 second at bus, at the generator bus, let's say, okay? I want to apply fault and I want to keep that fault for 3 cycles. That means, let's say 0.06 seconds. You can, it's up to you actually. Then I'll run the system with under faulted condition, okay? Then I clear the fault. Apply, now clear fault. See, it's on 2. When you click on go, it will be clear. Now the fault is clear. Let's run the system for another 5 or 10 seconds. Let's say 5 seconds. Okay. If you look here, this is the speed deviation. Basically, these are different values. The last one here is the speed deviation. If you look at the output bar, this speed deviation has got some high value, but it will be reduced. I'll show you. If you run it for 5 seconds. Yeah. So though it has not been reduced because probably, yeah, we can, yeah, like if you look at the other activities, activity 3, like I use the stabilizer that has been reduced. But if you look, I'll show you, that means you will get the response like here, the same. Sorry, let me open this. So at the end, so this is the speed deviation you will get. This is the channel file plot data, okay? But what happened in this current version, like I can open that out file. This is the out file, okay? But this plot function is not working here in this version. This channel plot is not working. Okay, that's the limitation I was talking. But if you are good in Python and all this, you can. There are some tutorials like you just put how to convert .out file into Excel file. You can easily convert it into Excel with 3 whatever the channel you have used with all those channel data. It will give you the similar thing like what you can see here. The PDF I showed you. The PDF I showed you, like I selected 3 channels in the tutorial one. Like you can select it's automatically count. But if this plot function here, plot book, it doesn't work actually, you know, it doesn't work because of this free version. It doesn't work actually. Okay, so even I am putting this channel file ruet.out, it doesn't work. Let me show you it shows or not. Yeah, let's say speed. I want to show you speed if it works. No, it's not showing. Yeah. No, it's showing differently. Yeah, it's not showing. Yes, it's showing differently. It doesn't show the time. Yeah, it doesn't showing the channel plot like as I supposed to show you time because it's not showing the time. Okay, so let me. Let me try again, if I could show you. Because there's a, because it doesn't have the time, okay? X-axis usually shows time, but it doesn't have the time, okay? Because of this version, But anyway, it will show the result like that, okay? It has got data, because when you see XY, it has got some data. If we encrypt the data, so we can plot all those things, okay? So this is the dynamic simulation, but you can do a lot of different things. If you just click on this, okay, linear network analysis, equivalent network, and you can do sensitivity analysis. Okay, you can do sensitivity analysis, one bus, let's say bus 3. I just covered some part of it, okay? Like with some data, like with respect to some data, you can do the sensitivity analysis, okay? So you can do many different things with this software. It's not only just the simulation, and you can have subsystem. And other thing that I didn't talk is like you can record, like when you click on this, you can use Python scripting and you can record all these events. You don't need to repeat the same thing. You can automate actually, okay? You can automate all this. But there is a bit more advanced level. Yeah, there is a bit more advanced level, but you can automate all these operations, okay? If you are an expert user, you can automate all those information. So that's pretty much I wanted to show you. And if you have got any question, yeah, we can discuss. And thank you for your attention.
Thank you so much, sir. It's
Okay.
time for question and answer session. If you have any question, you can either write it down in the chat box or unmute yourself and ask the speaker. You can speak in Bangla for your ease.
বাংলায় বলতে পারো বা পারে না কি, অনেক সিনিয়র থাকতে পারে বাংলা। যে কেউ সেলফ স্টাডি করতে পারবে আর কি, যে টিউটোরিয়ালগুলো দিছি যে কেউ সেলফ স্টাডি করতে পারবে। হ্যাঁ, যদি তুমি আগে ইউজ না করো, যদি ফার্স্ট টাইম ইউজার হও, ডেফিনেটলি মানে আমি যেটা বলবো যে ইউ আর ইন দ্য মিডল অফ এ সি আর কি। হ্যাঁ, মানে যত ডকুমেন্টস আর কি, যত ম্যানুয়াল যদি দেখো, যত ম্যানুয়াল, কারণ ডেফিনেটলি পাওয়ার সিস্টেম কমপ্লেক্স আর কি। মানে অবশ্যই তা অ্যানালাইসিস বলো বা যেটাই বলো, অবশ্যই কমপ্লিকেটেড হবে আর কি। হ্যাঁ, অবশ্যই কমপ্লিকেটেড হবে, কারণ তুমি আমি তো লিনিয়ার নন লিনিয়ার যে ইকুয়েশন গুলো দেখালাম, জাস্ট স্ট্যাটিক ইকুয়েশন। ইভেন মানে তুমি যখন হায়ার অর্ডার মডেল আমরা যখন করি, তোমাদের দু একজন টিচার আমার সাথে কাজ করে আর কি, তো ওরা কন্ট্রোল ডিজাইন করে হায়ার অর্ডার 7th অর্ডার মডেল মনে করো। তো জিনিসগুলো আরো কমপ্লিকেটেড। আমি তো জাস্ট সিম্পল থার্ড অর্ডার মডেল দেখাইলাম, ডাইনামিক সিমুলেশন পার্টটা আরো কমপ্লিকেটেড আর কি। তো আরেকটা জিনিস যেটা হয়তো মানে অনেকেই যেটা ভিজুয়াল প্রেফার করে, কিন্তু ভিজুয়াল মানে আমি যেটা বললাম যে স্ক্যাডা সিস্টেম থেকে ইউজুয়ালি র ডাটা করা হয়, তো ভিজুয়াল সিস্টেম দিয়ে যদি কেউ হ্যাবিচুয়েটেড হয়ে যায়, তখন সে আবার র ডাটা গুলো অ্যানালাইসিস করতে যায় প্রবলেমে পড়বে আর কি। হ্যাঁ, তো এই জন্য যেটা আমি ওই যে ডাটা কেস দিয়ে দেখাইলাম আর কি, অনেকে এই নেটওয়ার্ক কেস দিয়েও ট্রাই করতে হবে। নেটওয়ার্ক কেস যেটা সেটা জাস্ট ড্র্যাগ এন্ড ড্রপ আর কি, জাস্ট নেটওয়ার্ক ওই যে MATLAB Simulink বা অন্যান্য যে প্ল্যাটফর্ম গুলো আছে, জাস্ট ড্র্যাগ এন্ড ড্রপ করলেই হবে, জাস্ট কানেক্ট করলেই হবে আর কি।
জি স্যার।
তো কারো কোনো কোশ্চেন না থাকলে তাহলে আমরা ফিনিশ করতে পারি যদি না থাকে।